Hello, my name is Gabriel Ndow1 from the University of the Gambia, Department of Physics. In today's lecture, we're going to focus on our minds on the concept of circular motion, and in particular, uniform circular motion, and to try to understand the dynamics of that type of motion. It's an important topic in mechanics because it serves as a basis for us to understand many of the motions that we observe even with our naked eye, such as the motion of the merry-go-round that we see, the Ferris wheel, the motion of the planets, which we don't see generally with our eyes. We have to look through a telescope, but at least it helps us understand the physics behind the motion of the satellites and planets. And in addition, it gives us the basis for the models that we have in understanding the subatomic particles that move, such as electrons and so forth, that are captured within an atom. All right, so we shall try to understand the dynamics of it. First of all, we will assume that we're going to look at it from the perspective of a point particle, that this spoon is really, its mass is concentrated at the center of mass here. And I have a string here to just as a demonstration. You've probably seen this many times where we just rotate the mass that is attached to the string, and then we try to analyze the motion. Now, the reason why the object rotates around, because as we know from Newton's first law, if an object prefers to be at rest or move in a straight line, but here we see that the object is going to move in a circular path, which means that there must be an external force based on Newton's second law that is acting on the object for it to change its direction of motion. If it was going straight like that, now it has to turn and keeps turning that way. That means that there is an acceleration or force on it acting in a direction that is different from the one that it would have originally taken based on Newton's first law. Okay. For this uniform circular motion, that is, if we assume that the particle is moving with a constant speed of rotation, and also a constant linear speed, v, then in that case, we have uniform circular motion. And the formula is given from your Mechanics 1 class as A equal to v squared over r. It's a well-known equation. However, that acceleration that is causing the object to rotate is pointing towards the center of the circle as the object is moving. Whether it's in a complete circle or in a curve, it's the same concept that we're dealing with. Okay? So we have, if this is the pivot point or the center of my circle, right, as we rotate round, the acceleration at the bottom here will be pointing upward towards the center, and when the object is at that point, the acceleration will be pointing horizontally to the left, etc. So the direction of the acceleration then is always pointing towards the center of the circle as the object is moving. Now, what are the forces that are acting? We'll start with a basic thing. We assume that there are no external forces. We'll just take a simple consideration of the object just rotating around. If it's just the mass and the string attached to it, then the force that is causing that acceleration is the force that is provided by the string, the tension on the string. And that tension will be pulling towards, because we know that strings cannot push, but they can only pull. Cannot push, but they can only pull, right? That causes the tension. So as this object wants to free itself, it feels a tension, a force pointing towards the center. And that's the tension on it. According to Newton's second law, that force is equal to m times a, mass times the acceleration. But because that force is always pointing towards the center, it's an example of a central force, a center-seeking force. So in this case, that center-seeking force would be the tension on the string. Okay? And we have a special name for those types of forces that cause the object to rotate in a circle, and we call it centripetal force. Just as the acceleration is given a special name called the centripetal acceleration. Right? So when we write the equation of Newton's second law, F equal to ma, then the force would now be the centripetal force, which will be, in this case, the tension, and that will equate to the right-hand side, which would be the mass times the acceleration. But the acceleration here is the centripetal acceleration given by v squared over r. Okay, so that would be the various variables that we would be working with as we rotate the object. Now let's look at different other components or other dynamics of the motion. What if I was rotating the object vertically, such that its axis of rotation is pointing horizontal, right? So it's spinning around an axis that is pointing outward, meaning I'm going up and down like that, as opposed to the object moving around in a disk, in a circular path that is horizontal that way. Well, in that case then, when we think about it, if the object is close to the surface of the Earth, there are two forces acting on the object. One would be the tension on the string, provided by the string pointing upward. And of course, gravity always acts on any object near the surface of the Earth. So there's a force of gravity, its weight pointing down. So that would be the two forces acting on this object. Now, Newton's second law talks about the net force acting on an object. In this case, the net force, which is the sum of the forces, consists of two forces, one pointing up and one pointing down. Remember, forces are vector quantities, and the directions also count. So in that case, if I have my uniform motion again, my uniform circular motion as before, to analyze it properly, I have to consider these two forces that are now acting on my object. One being the tension on the string, and the other being the force of gravity pointing downward. So if I look at the object when it's rotating, let's say at the bottom, when it is for an instant at the bottom of the rotation, the circular path, at that point, the weight is pointing down, the force due to gravity, and the tension is pointing up. However, when the object reaches its maximum height, we see that there is no force pointing upward, because in that case then the tension is pointing down and the weight of gravity is also pointing down. However, remember the object is only there for only an instant in time. So really one could say that at that instant in time there is no tension, no pulling on the string. However, the force of gravity contributes to the downward force. Right? On this side, when the object is on the right-hand side, horizontal, then in that case we have a force of the tension pointing to the left, whereas the force of gravity is continually pointing down. Right? Now we have to consider, because the object is moving in a circular path, we will have to consider these two forces as the object moves continually and try to resolve or add these two forces together to get our net force. If the object is at an angle that is neither vertical nor horizontal, at an angle like that, then we see that in that case we have a tension pointing in an angle towards the center, whereas the weight is acting vertically down. So we have two forces acting, one at an angle and one vertically down in the y-axis. Again, we have to take the net force to really analyze it properly and understand the motion. Okay? That's the exercise that we wanted to demonstrate, that these are the concepts that come into play, right? That is the exercise that we wanted to cover today, and more material is available online at the AVU website. Thank you.